Okay, let's continue our discussion. Okay, in the previous class, we looked at affine transformations. Okay, and we have seen that we verified that affine transformations obey reflexivity and symmetry.
Yes.
Okay, and we have to prove the transitivity to show that affine transformations are equivalence relation.
Yes.
Okay, the symmetry condition was particularly interesting because the symmetry condition forces us to define an inverse transformation. Okay, and then we found the condition for the inverse and we modified our definition of affine transformation by including that condition. Okay, let me share my board and okay, Joe, can you see the board?
Yes.
Okay, now this was the symmetry condition and the condition for inverse was this, isn't it? Yes, AD minus BC not equal to 0.
There should
and
be a inverse for the
transformation. That is in order for the transformation matrix to have an inverse, its determinant should not be 0. And that condition is given by this equation.
Yes.
Okay, so we modified our definition.
Yes.
By adding this condition also. This condition is a requirement for a transformation to be for being an affine transformation. Okay. Since we are dealing with real affine transformations, all of these numbers a, b, a, comma b, comma e, comma c, comma d, comma f, all of these should be real numbers.
Okay.
That is also a condition here.
Yes.
Okay. We have to, that is a prerequisite assumption, right?
Yes.
But when we move on to complex numbers, these all numbers can have complex values that we will discuss when we discuss complex affine transformations. Anyway, we will continue our discussion to proving the transitivity of affine transformation. Okay, transitivity. Okay, for transitivity, let's assume we have a transformation from a coordinate system A to another coordinate system B. Let's say we have a coordinate system here. Let me draw some kind of coordinate system. And we have another coordinate system, say this one. Okay. Okay, some rotated coordinate system or something like that. This is B, this is A, and this coordinate system is B. And then we have another transformation from B to some other coordinate system. Some say we have scale. Let's say we have scaled the axis. Okay. Okay. This was this coordinate system.
Okay, I have a small doubt.
Okay.
So from A to B, you are rotating. And from B to C, we are again rotating backward. Are we rotating it backwards?
Oh, that's a very, very good observation. Okay, okay. So we have to, okay, if we are considering this coordinate system, this is an actually inverse transformation.
Yes.
Inverse transformation. Joe, that is a very crucial observation. Because that means you are observing carefully. Okay, that's a good thing that you've pointed out that correction. Okay, let's say we then scaled this coordinate system. Incredible observation, Joe. Incredible. Really, you are at that means you are really attentive in this class. Okay, so the credit goes to me also. Okay. Okay, so I don't know, maybe let's scale this coordinate system into some, and this transformation is from B to C. Okay.
Okay.
A to B and B to C. A to B, this is from A to B. A to B, and this is from B. This is from B to C. B to C. Okay. For transitivity, we have to show
A to. If A to B is X and B to C exists, then A to C also exists.
Exactly. We have to show the transformation from A to C. This is what we need to prove. Okay.
Okay.
Okay. So let's assume the transformations. Assume transformations A to B and B to C.
Okay.
We have to prove A to C. Okay.
Okay.
Let's say this is a XY and this is UV and this is some ST, some coordinate system. Okay.
Okay.
So we have the coordinate transformation x comma y to u comma v.
Okay.
Given by the usual definitions, u equals ax plus by plus e, isn't it?
Yes.
And v equals cx plus dy plus f.
F. And
And
the okay, what is the coordinates of the third one? S is equal to
s and t.
okay.
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 Okay. Okay. This is our coordinate transformation from x comma y to u comma v given by these equations.
Okay.
And we have the condition AD minus BC should not be equal to 0. Okay.
Yeah.
And let's consider the transformation from this is from A to B, isn't it?
Yes.
And now let's consider the transformation from B to C, that is from u comma v to s comma t.
Okay.
Given by equations S equals say capital AU plus
Okay.
BV plus E. Okay.
Yeah.
And T equals CU plus DV.
DV plus capital F.
Exactly. Okay.
Where AD minus BC not equal to 0.
BC not equal to 0, and all of these are real numbers. Okay.
Okay.
Real meaning if you are computationally oriented, we are talking about rational numbers. Okay. If you are
Floating
putting
points.
into if you are floating point numbers, if you are putting this into coordinate not coordinate, some calculator, only some computer algorithms or something like that. Okay.
Okay.
Okay, so we have to find the transformation. This is a transformation from B to C. So we have to find transformation from A to C. For that, okay, let's substitute the values of u and v in this equation. From this equation to here.
Okay.
Okay. So we get these equations become S equals. Let's assume, let's give these equations numbers. This is 1 and this is 2. Substitute
1 and 2.
1 into, okay. Okay. So that S equals A times, what is U from 1?
So S is equal to 1 second. S is equal to capital A into AX plus BY plus E times capital B
plus not times, plus
B
times
B times CX plus DY plus F.
Yeah, CX plus DY plus F plus
Capital E.
Okay, and T becomes
capital uppercase C times AX plus BY plus E close the bracket into D times Cx plus dy plus small f close the bracket times f.
Plus f.
Yes.
Okay, let's distribute these a, b, and c inside the bracket. So we get s equals a times a. Okay, Joe, tell me
Yeah.
what's the answer.
Okay. So, that will become 1 second. S equals 1 second. Let me. S equals a times a x plus a times small b times y times capital A times E plus b times small c times x plus b times small d times y plus b times f plus capital E, and t is equal to, yeah, got it. I'm getting an idea how we got it. C times a times x plus c times b times capital C times b times y plus c times E plus d times c times x plus capital small b y plus d times f plus f. So we take the terms of x's together, isn't it?
Exactly.
A times a plus b times c into x plus a times b times b times d into y
plus
ae plus bf plus e.
exactly. Put these terms inside a bracket also.
Yeah. Then the other term will become c a plus dc times x plus cb plus dd times y plus
cb, right? Cb plus dd.
yeah
Right?
yeah plus ce plus df plus f. Okay.
This is actually a affine transformation from x comma y to s comma
T.
Okay, let's name this. If we name a plus b c as, I don't know, what numbers we shall put? K, I don't know, K. Okay, and a b plus bd as L, and a e plus b f plus e as O. I'm putting this as O. And then CA plus DC as M.
Okay.
And CD plus DD as N. And CE plus DF plus F as P. Substitute. Okay, substitute. For these values, we are substituting K, L, M, and OP. So we get S equals, K times x plus, this is small s, this is a variable, k times x plus l times y plus o, and t becomes mx plus ny plus p. Okay, this is a
we cannot say we cannot say it's an affine transformation.
Why do?
We have to check whether k AC minus VD km into minus ln is not equal to 0.
Okay, that condition is have to satisfy.
Yeah.
Okay, we have to. Okay, that's let's check that condition. That is a very good. Let's check that condition. Okay, k times kn minus l times n, right? Becomes
AD minus BC, yes.
So that is a very tedious calculation. Do you want to do that?
Let's check. Okay.
Really?
No, I don't want to do it really, but you know, you got the idea, isn't it?
Okay, you got the idea, right? Okay, if anyone wants to do it, do the tedious calculation and check whether it is. If you think about it, doing such algebra gives us so much pleasure, isn't it? It is actually fascinating to just multiply and add and do these high school level stuff. But do you want to do that?
No, I don't want to do that.
Okay.
No, we can do it as a. You can check. We can say that you can check
We
for
can
yourself.
let's give that condition here. Okay.
Okay.
K, and if I'm.
We have to prove that KL minus.
You know, to be frank, I haven't even checked this. Okay, this is Kn minus Lm, right?
Yes.
Should not be 0. Okay, anyway. Okay,
we have to prove that.
This is a homework. Prove it. Okay.
Yes.
Okay, that's it. So we have shown that this is a transformation from x comma y to s comma t, that is from A to C. This proves the transitivity.
Yes.
Transitivity. Okay. This means that affine transformations are equivalent solutions. That is, affine transformations are equivalent relations. Okay. Okay.
Okay.
Okay. Now let's say we have a set of since we are studying conic sections, let's say we have a set of conic sections, and we are defining this equivalence relation, this affine equivalence relation, this affine transformation, which is an equivalence relation. We are defining that relation on that set of conics.
Okay.
Okay. What will be the equivalence classes of that relation?
It will be another conic.
That we will not get into that today, but we have to discuss that thing because that's an intriguing idea, right? Because if affine transformations are equivalence relations, and if we define that equivalence relation to a set of conics, what will be the equivalence classes? That is a very interesting question, but we will return to that question later. Today we shall continue and look at another important thing here. Okay. Okay, we have seen that affine transformation are equivalence relations, but can we see affine transformations as linear transformations? Because affine transformations is found out by matrix multiplication, isn't it?
Yes.
So there is a linear algebra involved here.
Okay.
So That's another important question. Can we see affine transformations between two coordinate systems?
Coordinate system or
The coordinate systems.
Hmm.
Yes, between two coordinate systems
Yes.
as linear transformations. Can we see that? That's the question here. Linear transformation. Actually, the answer is
Yes.
yes, except one. The answer is yes, except one. One affine transformation can never be considered as a linear transformation. For that, let's go back and see our original notes. Okay, can you see this note, this page here?
Yes.
This was a change of origin. Okay.
Yes.
We have looked at various kind of affine transformation. We have looked at change of origin. We have looked at a rotation, and I think we have looked at also scaling of axis, right?
Yes.
Okay, there is also reflection and many these kind of and combinations of these kind of transformations are also affine transformations.
Okay.
But this one is in this very peculiar kind of transformation. This except the change of origin, rotation, scaling, reflection, all of these preserve the origin. Okay.
Okay. Okay.
Okay. What is a linear transformation? What is a linear transformation between two vector spaces is okay. Let's what is a linear transformation? Let me add a pen. Before that, uh, what is a vector space? A vector space is essentially a group. Vector space is essentially an additive abelian group. Think about it. Every vector has an inverse. Okay. And when we add two vectors, we get another vector. So let me write here.
Okay, so first you have to, since this is an introductory course, first you have to define what all these terms are. What is additive, abelian group, and all those things you have to define.
Okay, let's do a comparison between groups and vector space. Okay, groups.
Okay.
First is if G1 and G2 are elements of that group, then G1 times G2 should also be element of that group.
Yes, the G times means any operations.
Times mean the binary operation that defines the group. Group is essentially a set with a binary operation. Okay.
Okay.
That binary operation can be addition. It can be depends on the context. This is actually groups. These algebraic objects are abstract objects. It can be anything. Rotation, reflection. Depends on the
should it be binary operations?
Yes, but that's binary operation between two objects.
Between two objects. Suppose if you take a equilateral triangle as an as a group, rotating the equilateral triangle is actually a operation, but it is not a binary operation, isn't it?
Yes. It is a triangle is not the element of the group. The rotation group, in a rotation group, the elements are the rotations itself. You are composing two rotations.
Okay, when
that's another story. Okay.
Yeah.
Let's not get too deep into because this is not exactly our topic. I'm just let's discuss this because it's an informative idea. Okay. This is actually true for vector spaces also, because if let's assume a vector space V with a vector addition plus. Okay. If V1 and V2 are elements of that vector space, then if we add to those two vectors V1 and V2, that vector will also be in that vector space. Okay. So the first property is common for both. So what is the next property? This binary operation should be associative, meaning G1 times G2 times G3 should be
element of
No, should be associativity. To prove associativity.
G1 times
G1 times
G2 times G3.
G2 times this is G3. Okay, G3. Correct. This is same with the vectors because vector addition is also associative.
Yes.
V1 plus V2 times V3 plus V3 is equal to V1 plus V2 plus V3. Okay, then the third condition is, what is the third condition? Existence of inverse for every group element. Okay, for all G element of this group, there exists a G inverse such that G times G inverse will give the identity. Okay. This is also true for vectors because every vector has an inverse vector. Just reverse the direction of that vector with the same magnitude.
Yes.
Right?
Yes, you got it. Yes, you're right there.
So that means that vector spaces have inverse for every vectors. This is same for vectors. For instance, if V for all V element of V, there exists a negative V such that V plus that negative V is equal to the null vector. Okay. So what is this identity? We should have defined that identity before defining inverse. What is that identity? What is it?
Any vector, any operations done on the if a member of the group is being under any operations of the vector, then you will get the same vector itself.
No, not vector. We are talking
about same element itself.
Yes, for all G belong to that group, when we perform an operation with an identity, we get that same element. That is the existence of identity. Okay, this is identity element. Here also the condition is same, that identity is the null vector, because 0 plus any vector will always give that same vector. Okay, this is called a null vector. What is another name for null vector?
Identity vector? No. Zero vector.
Okay, that is also null vector. The other name for null vector is origin.
Oh yeah.
That is peculiar here. Origin. We are talking about change of origin here, isn't it?
Yes.
Okay, this means that vector spaces are also groups. Okay, this means that vector spaces are also groups. This means that vector, let me write it more clearly. This means that vector spaces are also groups. Okay, they are not just groups. There are additional another important property, which is the multiplication by a field element. We are also known as scalar multiplication. Okay, because when we multiply a vector with a scalar, we get a vector in that
same direction but magnified
within that same set. Okay, but
within
for a group,
that same set
meaning within the set of vectors. When we multiply a vector with a scalar, we get another vector.
Yeah. Okay.
But there is no multiplication with a scalar. The multiplication by a scalar with a group element is not defined.
Okay. Yeah.
Okay. When we define multiplication with a group element, we get a vector space. Exactly. That scalar should be element of some number field. Okay, number field or some field. Okay. Anyway, vector spaces are also group. This means that vector spaces are also group, and very important, linear transformations are are group homomorphisms. Very important.
Okay, so you need to define what group homomorphism
Group
is.
homomorphism means, let's say, let G1 belong and G2 belong to a group G. Okay. And say H1 and H2 belongs to another group H. And we are defining a map from function from G to H.
Okay.
Okay. Under that function, G1 is mapped under that function. G1 is mapped to H1.
Okay.
And G2 is mapped to H2.
Okay.
Then, if this is the case, then G1 plus G2. Then G1 plus G2 should be mapped to H1 plus H2.
Okay.
If meaning similar algebraic structure, homomorphism defines similarity in algebra. Because
Okay.
let's say we have two vectors. Let's say we have two sets here, 1, 2, and 3. Another set here, A, B, and C.
Okay.
And if we map A1 to A, 2 to 3, and 1 plus 2 is 3, right?
Yes.
If
so
1 plus 2 is
then A plus B should also be
equal to C. That's it. Okay.
Okay.
What is H1? H1 is actually f of G1, right?
Yes.
H1 is f here alpha.
Yes.
Okay. This is
Alpha.
so alpha of G1 plus alpha of
G2.
That's it. This is homomorphism. This kind of a map is called homomorphism. And if such a map exists between two groups, we say that those two groups are homomorphic. Homomorphic. Okay. We are talking about groups.
Yes.
These are group H and G are groups. Okay, that is alpha of G1 plus G2 gives alpha of G1 plus alpha of G1 plus alpha of G2. This is the homomorphism condition. This is the definition of homomorphism.
This is also true for linear transformations.
Why? Because linear vector spaces are what?
Linear transform. Linear. Are also groups. Homomorphic groups.
Not homomorphic groups. Vector spaces are groups. If two vector spaces have a linear map connecting them, we can say that
they are homomorphic.
Linear transformations are vector space homomorphisms. That
okay.
Linear transformations are
better.
Linear transformations are vector space homomorphisms. Meaning if let's say a linear transformation exists between vector space V to vector space U, okay, or I don't know. Let's okay, let U to U, V to U. This V and U looks so similar. A and B. Okay. Okay. Vectors linear transformations are usually denoted by T. Let's use alpha. Okay. This means that if A1 and A2 are vectors in A, right? And
B1 and B2
and B2 are vectors in B. And this transformation alpha of A1 is B1.
Yes.
And alpha of A2
is B2.
Then and if we add, then alpha of these two, sum of these two vectors, A1 and A2,
alpha of A1 plus A2 should be equal to alpha of A1 plus
that
alpha
is V1 plus V2. That is V1 plus V2. Okay.
Yes.
Also, since we are talking about vector spaces, there is linearity condition should also be obeyed here. That is okay. Let's talk about linear. Let's first finish this equation. This means that alpha of
A1
plus alpha of A2.
Of A2.
Okay.
In more general way, if you multiply it with a scalar, we can say that.
Okay,
Let's
that's
say
another condition. That's not a generalization of this condition. That is the linearity condition. Let's write this. Let's write alpha of A1 plus A2 equals alpha of A1
plus
alpha plus alpha of A2. This is the homomorphism condition or linear transformation condition.
Okay.
Definition. Let's not try. There is also another condition should also be included here. That is, let's say we have let's say we are multiplying this A1 with a scalar K.
Okay.
Right? And that product should be mapped to K times alpha of A1. You get the idea?
Yeah.
Because if this is a set, this is our first vector space A, and
actually,
A1 is an element in A.
We should start from these vectors and groups and all those things, because if we start from there, then these affine transformations, these things will make more sense there.
Okay, no. We are not talking about affine transformations in the context of linear algebra. This is just a demonstration of why affine linear maps should preserve. I'm actually trying to write a proof showing that a linear transformation should always preserve origin.
Okay.
If that is the case, we can see that change of origin is not a linear transformation. That's what I'm trying to prove here. To show that I'm just making a comparison between group theory and vector space. Just I'm defining. There is no need to go into group theory. If being honest.
Okay.
I'm just writing here to understand the context which we are talking about. Okay. The only thing is linear transformation. I should have just gone directly into linear transformation. But if you want to understand the complete context, you can just review it later. Okay. Anyway, let's assume A1 is the element of this vector space, and say B has a vector. If there is a homomorphism alpha, linear transformation alpha, and A1 is mapped to B1. Okay. Which is B1 is alpha of A1, right?
Yes.
And if you multiply A1 with a scalar, let's multiply A1 with a scalar, we get to KA1, right?
Okay.
And that is also an element of A1. That is a definition of vector space.
Yes.
Okay. If that is the case, this alpha should map alpha of K times A1 to K times B1. Similarity in that linear property also. Linear transformation should also preserve that property. Okay.
Yeah.
Meaning B1 is alpha times. What is B1?
B1 is the vector in the H.
B1 is vector in the H, which is what is B1? B1 is alpha times
A1. Okay.
Right? Yes. And what is alpha of KA1? What is alpha of KA1? K times B1. K times B1. K times B1. Right? What is B1 from this equation? B1 is
alpha times A1.
So alpha times KA1 becomes K times alpha of A1. That is how K got out of here. Okay. This is similar. The algebra should be similar. Okay. That is the essence of homomorphism. Whether it is linear transformations or homomorphisms, group homomorphisms, along with this linearity property, meaning multiplication with a scalar should the scalar should come out. Okay, this is also called as the F linearity. If this K is an element of some field F, something like that. Okay. Anyway, that is the idea of linear transformation here. Now, this linear transformation should always preserve origins. That is the idea here. Linear
Okay.
transformations or homomorphisms. Homomorphisms always maps identity to identity. To identity. That is, let's say we have vector space or groups. Vector space are also groups. And here the identity is EA. Let's okay.
Okay.
If we are we can also write 0A. What what is your preference here? E or 0?
E of A.
Okay, E of A.
Oh. E of
Okay,
A or identity of I of A.
okay, anything. Okay. E of A will, if alpha is a homomorphism from A to B, or if we're talking linear algebra, a linear transformation from A to B, alpha should map identity to identity. E of B.
Okay. Okay.
That is that we can prove this. Okay, I'll show this. Okay, that is, we have to show that alpha of E1 EA is equal to E of B.
B. Okay.
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 What is the property of EA, Joe? When we multiply EA
EA times
or add,
another.
let's add. We are talking about
Okay.
vector space. Let's add vector space. This is actually origin, right?
Okay.
Origin of A. When we add with the origin of A itself, we get what?
EA.
EA, right? Similarly, if we add origin of B
With
plus
origin of B, you will get B itself.
origin, it's that origin. And also, if we add A vector with that origin, we will get
that vector itself. A itself.
Okay. Similarly, if we add vector B with the origin in B, vector space B, we get vector B. Okay.
Okay.
Let's consider this equation. EB. How should I prove this actually? EB plus EB equals EB, right?
Yes.
Okay, let's consider an
this
no,
actually it comes from the all these things comes from the definition of identity itself, isn't it?
identity. Okay, but we have to prove that that identity should be preserved under homomorphism. Meaning we have to prove this relation. Alpha of EA should give EB. That's what we have to prove.
That's simple.
Okay.
Take the transformation of that equation.
What equation?
Alpha of
okay.
A plus EA should be equal to alpha should be equal to alpha of A plus alpha of EA.
This is a homomorphism condition.
Then it will become alpha of A is B, isn't it?
Alpha of A is B, correct? No,
okay.
no. We haven't defined that. Do you want to define alpha of A as B?
Yeah. If you are defining, alpha of A as B.
Okay, that definition should be given here. Let's assume that is an assumption. Alpha of A should be B. Okay, so B.
Isn't it? Alpha of A is equal to B, isn't it? So this is B plus alpha of EA, isn't it? Now, if we look at the in the LHS, LHS, then we can say LHS will become alpha of A itself, isn't it? By the definition of identity operator.
Yes, exactly.
That's,
okay, alpha of A.
Okay, then this is alpha of EA. So this is, we will get B is equal to B plus alpha of EA. So alpha
what?
of
This is
yes,
yes.
alpha
Right. Joe, you're correct. This can be written as A equals B plus alpha of
of
EA.
EA.
Yes.
Then alpha of A can be written as B.
So B equals
B plus alpha of EA. Alpha of EA. So alpha of EA should be the identity operator of B.
exactly. We shall compare this with yes.
Isn't it?
We can compare this with this equation,
Yes.
right? So
Yes.
on comparing with correct, Joe, the proof is correct. On comparing with B plus comparing with
B plus EB.
let me write it here. On comparing with B equals B plus EB. We get
Alpha of
EA
should be equal to alpha EB.
Exactly. Okay.
Okay.
This means that homomorphism preserves identities. Or under a linear transformations, the origin must coincide. Or this is origin of A, and this is origin of B, right?
Yes.
Or under a linear map, origin must coincide. Okay. That is, which means that a change of origin is not a
linear transformation.
Which means a change of origin
It's not a linear transformation.
Is not a linear map. Very important. So that is actually evident from the relation, the definition equation. Because let's look at let's go back and check our original board here. This was the the change of origin was given by this equation. Do you remember?
Yes.
Okay, let's copy this. How can I select all of these things? Okay. And let me paste it here. Okay. Okay.
Okay. Here we are changing.
Okay. This is evident because we here this is a transformation from x comma y to u comma v, right?
Yes.
Let's put x comma y as the origin here, meaning put x equals 0 and y equals 0.
Okay. Then
then
u will be negative a.
u and v becomes minus a and minus b. That is u equals minus a and v equals minus b. If it was a linear transformation, when we put 0, 0 in xy, you should get u equals 0 and v equals 0. Okay? You understand the idea?
Yes.
This vector just represents a translation. Okay? Not, this is not an origin. Origins do not coincide. Do not coincide. But if you look at multiplication, by only multiplication, meaning let's look at a linear transformation without the change of origin. Okay? Affine transformation without change of origin. Affine transformation.
Without. So actually what happens is that
without change of origin. Okay, so for instance, let's consider this u v equals a b c d times xy.
okay.
When we put x equal to 0 and y equal to 0, we get u v becomes
0 itself.
0 0, which is the null vector for the, that is u equals 0, v equal to 0. Origins coincide. That is, this is a linear transformation. Therefore, is a linear map. That is a very interesting idea, right?
Yes.
Because when we perform a change of origin, that affine transformation is no longer a linear. Okay.
Okay.
All the other affine transformations are linear maps. They can be performed by a matrix multiplication. But a change of origin can never be achieved through a matrix multiplication. We have to add vectors.
Something.
Okay, Joe?
Yes.